Hello, everyone, and welcome to today's webinar. I would first want to welcome all of our colleagues from Ziegwerk, but also especially to all of our external attendees from all over the world today. We are very pleased that you're able to join us today. And today our speakers will be discussing the recyclability of monoplastics. Before we get started, I'm going to just go through some housekeeping to ensure that you can interact with myself and also with the speakers. We have unfortunately had some technical difficulties with the webcam today, so they don't have access to the platform. And as a result, we will unfortunately probably not be able to turn on our webcams today, but we are hoping to have this issue fixed before the next webinar. So we do apologize for that. Secondly, all attendees are automatically muted. So if you wish to ask the presenters a question, please type your question in the question box, not in the chat box, because it's very difficult for us to monitor both. And then the presenters will answer as many as possible during the Q&A session at the end of the session. If we do not get to your question, we will try to follow up with you directly after the session. In the event that we experience any technical difficulties, please do stay online and wait for further instructions. A recording of this webinar will be made available to everyone. And without further ado, I would now like to welcome our speakers for today, Dr. Björn Ewig and Dr. Stefan Busse, who will introduce themselves and their presentation.
All right, welcome everybody. Thank you very much, Carla. My name is Björn Ewig. I'm the head of technology for flexible packaging in the region EMEA here. And together with my colleague Stefan Busse, we would like to show you today how you can be successful in making flexible packaging recyclable. And this, of course, with the support of Ziegwerk products and technology. And in the first part, I will talk about how you can secure the performance of your packaging when you move from a multi-material to a monomaterial packaging. And then in the second part, Stefan will show you what you can do to overcome the technical challenges of mechanical recycling and mitigate downcycling. I think there will be enough time for questions in the end. So please keep typing them in so that we can answer them after we finish this presentation. Now, before I jump into technical details, please allow me to briefly remind us why we are doing this here and why we are talking about plastic. I think you're all aware about the so-called plastics paradox. The plastic paradox basically means that on one hand, plastic is a preferred option to address what we call here the global challenges. So that's symbolized here by the sustainability goals of the United Nations. So plastic is really a unique and versatile product with properties that make it best suited to protect our food and hygiene in the most efficient way that we can think of. And thereby, it enables our well-being, the well-being of mankind basically today. But on the other hand, we all know these horrific pictures of ocean littering, plastic cluttering beaches, fish dying, dolphins dying because they've digested or not digested, eaten plastic. So we have a serious problem with plastic leaking into the environment. So we can't do with plastic, but we also can't do without plastic, because then our whole hygiene and food concept would just crash. So what is the way out of this dilemma? The way out of this dilemma is that we have to rethink our economy model. We have to change our economy from a linear to a circular model. And in order to do this, we have to learn how we can reduce the usage of plastics, of course. So there are trends like paperization that I want to mention here. We also need to learn how to reuse plastic more often. And maybe one or the other of you already has a cup, a permanent cup that you bring for the coffee to go in the morning or something like that. But above all, we as an industry, we have to learn how to recycle plastic more efficiently. And when we talk about recycling, what do we actually mean? What are we talking about? There are a couple of principles of recycling that are currently discussed and are in the market, at least partly already. One very popular one is the one on the top here. That's the so-called chemical recycling. In chemical recycling, in principle, you replace crude oil by plastic waste. So you use the plastic waste as it is, you heat it up to very high temperatures in a cracker that is as big as a crude oil cracker, and you break it down into smaller molecules that you then can use to feed the normal chemical chain again. Big advantage here is you can use almost unsorted plastic waste. There are some exceptions, because some ingredients might still poison your catalyst, but in principle, it's very versatile. But it has two big disadvantages. Or maybe the biggest one is there is no cracker yet, and the reason is it's a multi-billion dollar investment that takes many years for planning and construction. And once you've done that, you will realize that also the carbon footprint of this method is not very good, because you have to heat the plastic waste to very high temperatures and you're burning part of it in the process. So you're losing material. So it's in that respect, it's not ideal as a recycling process. Another process that is pretty popular, at least in discussions, is a so-called solvent-based recycling. In the solvent-based recycling, what you do is you take your waste and you put it into a special solvent, and this solvent dissolves only one type of the plastic in the waste. So it's kind of a chemical sorting of the plastic waste. Nevertheless, it's more efficient when you have sorted plastic to begin with, because whatever doesn't dissolve, you have to somehow get out of the solvent before you evaporate it to recover the plastic that you want to recover. It is a little smaller in capex, but you can see from the picture here, still a sizable plant that you need. And it's also costly, because you have to evaporate the solvent. It takes a lot of energy, and that also gives you a mediocre carbon footprint. It's still not as bad as in the chemical recycling, but also not very good. So today, to my knowledge, there's no commercially feasible solvent-based recycling on an industrial scale. So that leads us to the third method here, and that's the mechanical recycling. You're all familiar with, I'm pretty sure, because it's already established in the industry. It's a very simple process. You take the plastic waste and you put it basically into an extruder, and you re-extrude it, and then you have a granulate that you can work with for new packaging or other plastic goods. It has a very low carbon footprint, because all you need is the energy to melt the plastic, which is comparatively low, and it also has a low capex, because such an extruder is much cheaper than the other plants that we have discussed earlier. But it, of course, like everything in life, it has a very big disadvantage, and that big disadvantage is that you can only use monomaterial in this process. As soon as you try to mix different plastic types, the result is terrible, and the quality of the recyclate that you get out there is so low that you can't make anything of value out of it. So this is where we are. We have mechanical recycling established, but that means we need to feed it with monomaterial waste. So that has serious implications on the way we build our packaging. if we want to go down this road. You're all aware that today we have very nice multi-materials, multi-layer packaging, duplex, triplex, even more complex. And we need to move these structures now to monomaterial structures. Those structures can be laminates, but since you're not combining different types of materials anymore, you might want to go to surface printed structures altogether, which makes it then, let's say, commercially even more attractive. However, that is much easier said than done, and you know that, because we are not using these multi-material structures because we're all technical nerds and we like complex structures, because they give us the properties, or the packaging, the properties that we need for distribution, for protection of the goods, for presentation in the shop. And this is a huge challenge to keep these properties when you now go to monomaterial. And there's no one silver bullet to solve these issues. But I'm pretty sure that if we work together as an industry, we meaning from the brand owner who thinks about different designs, the converters for the printing process, the film manufacturers, the ink manufacturers, the machine manufacturers, we will be able to overcome this challenge. I'm pretty sure, and there's also no alternative. So we have to overcome this challenge. In Siegwerk, we are working on this challenge since quite a while, and we already have developed a couple of solutions that enable this transformation. One challenge that you have is when you change the web you're printing on, you will have different requirement regarding adhesion and bond strength for this new web. And this we have tackled some time ago. So we have inks that are optimized for that and that work on these new monomaterial films and give you an excellent adhesion and bond strength. We are also working on oxygen barrier coating, and we're not too far away from a commercial solution there. For now, you might want to work with Alox or Ziox coated monoolefin films. When you do this, you will probably notice that they can be very brittle because the olefin film is still more flexible than the PET that you've used in the past. So it's difficult to work with, and therefore we have developed protective coatings for these Alox and Ziox films to make it a little easier to work with them. And what you will see mostly are challenges related to the surface properties of the new film structures, because this is what you change. You change the film on the surface, and all of a sudden you have different rub and scratch resistance, in particular when you go to surface print from lamination. This can be a big challenge. Your COF, your gloss, everything is different, and in order to correct that and to get you back into a manageable area, we at Siegwerk have developed a whole range of overprint lacquers. And these overprint lacquers can secure the performance of these monomaterial structures so that you can actually replace the multi-material structures with that. And there is one nice example that I'd like to show you here because it's also easy to show. That's the heat sealability. And I will demonstrate what Siegwerk can do for you here with a few clips. What you will see here in a second is we have put a film between two aluminum layers, and then we put these aluminum film sandwich, we put this in our little sealing device here. It's a lab device, and the aluminum is only there to protect this little sealing device because our co-worker didn't want to clean the device after each trial. And here, as a benchmark, we put in PET. And oops, sorry. Now it works. And the sealing condition is 160 degree, 1 second, 300 Newton. And you can see the employee opens the aluminum film and takes out the PET film, no problem. And this is not surprising, because 160 degrees is not very challenging as a sealing condition for PET. However, when you try this with MDO-PE, one of these new MDO-PE films, and this is exactly the same procedure. So the film is between two aluminum layers. Now he takes it out and he tries to open it. And you will see that he's not able, or almost not able, to get those aluminum film layers apart, because the MDO-PE film has basically turned into an adhesive, heat-sensitive adhesive. So no way that you could seal that in any way. Now, what we've done next is we have covered one side of this MDO-PE film with our OPV, our special heat seal resistant OPV. And we repeat the same process, again 160 degrees for 1 second and 300 Newton. And you see that he can now easily open the aluminum again, but when he tries to remove the strip from the other side, it's glued, it sticks to the aluminum, it tears, he can't remove it. And this is because the side that was covered with our heat seal lacquer did not adhere to the aluminum, but the unprotected side, of course, is still gluing to the aluminum under these conditions. So you see, we can make a big difference in the machinability of such a structure just by applying this heat seal lacquer, for instance. And this is not only theory and a nice lab result, but it's also used in practice in the industry already. And I'm showing you here an example from Chile for frozen food. And there, our customer, together with us, has moved a structure PET, PE, with colors and white in between, a laminate, to a surface print on white PE covered with a 2K OPV. And this 2K OPV gives the required heat seal resistance to give the machinability that the customer needs. But it also guarantees the deep freeze performance and the high gloss that is required to bring this product to the market in Chile. So this is already, as I said, in the market, it's done, it works. And this is another example that I'd like to show you. This has nothing to do with the heat seal lacquer, because it's a laminate, but still a nice example. And this time it's also an example from Europe. It's for dry pet food in Poland. And there our customer, together with us, moved the structure from a PET PE laminate, which contained PVC-based inks. So this is basically the worst case for mechanical recycling. We moved this together to MOPE laminate with colors in white in between. And here the challenges were different. We needed to have high initial adhesion and also very high bond strength in order to make this packaging stable. But on top of that, we also needed excellent print quality, because this cat is a very challenging picture. And the consumer will only buy this food if that cat is really flawlessly. Okay, with these examples, I conclude my part of the presentation. And I now hand you over to Stefan, and he will talk to you about how you can overcome the challenges of mechanical recycling. Thank you very much.
Yeah, thank you, Björn. Now let's have a look together at what happens when monoplastic packaging material eventually gets recycled. And just imagine bales like here on the left-hand side of collected and sorted monoplastic material, which at the recyclers is then washed and heated up in extrusion process to form the pellets that you see in the middle, either recycled polyethylene or polypropylene, depending on the value stream. What is the technical challenges? You can see on the right-hand side and in the traffic light logic. So the reddish ones are even more critical. Yellow, orange, or green could be probably more tolerated, but there's differences. So the challenges is the formation of gel particles or black spots. Sometimes they're so-called fish eyes in the recycled material. Then we have to face, of course, differences in the mechanical properties of a re-extruded film once we form a film compared to virgin material. It's about odor, also the presence of hazardous substances. If we recycled all the print designs, all the colors together with a monoplastic material. And there's also challenges like the coloration by the colored pigments, or if you look at transparency, homogeneity of the film, sometimes you have to face a certain haze and make some compromises in the end if you want to go ahead. So that's the challenges. We as Siegwerk believe if now we want to recycle monoplastic material, that there's principally two ways. One is with the inking, and on the right-hand side you can see is without the inking. The inking thereby means that you literally wash off the inks, the printed design, prior to recycling, prior to re-extruding the plastic film. And if you look at the left-hand side, what is the advantages with the inking in this process? It is certainly that we become independent of the ink chemistry because you wash it away. Due to the fact then no more pigments are available, there's also less or hardly any discoloration, which is a benefit. Of course, the de-inking process would bring a higher cost or higher effort because it's a process which is yet not established in the industry on a wider scale. And let's say on this background of higher cost, the success of this way and also the implementation in the industry will certainly depend on legislation and developments there, in the sense that only by, let's say, some fees in favor of packaging material which would be de-inkable, you could develop this de-inking process. If we look at the right-hand side, if we go without de-inking, which is possible and more with less investments necessary, the challenge is that the standard inks of today lack thermal resistance and stability, and I will come back to this in a second. Due to the fact that the pigments are still, or the printed design is still on the plastic film in the re-extrusion process, the discoloration is unavoidable and will be much stronger. And in the end, regardless of the challenges you have seen also on the chart before, still this material, the quality which you can achieve might be sufficient for a few or some applications, but of course the constraints are much higher compared to the inking path. Before we look now more into the thermal stability of inks and how Siegwerk can help to overcome this, let's have a briefly look into how printing inks are formulated in general. As you can see here, one of the major ink systems, solvent-based inks, is primarily formulated with solvents, And then you see 3 different raw material classes to a similar extent, which is the additives to fine-tune the performance of the different ink films. Then there's the pigments, which give the different colorations of the different printing inks. And then there's the so-called binders, which is polymeric systems, which help to fix or to make pigments and additives printable, if you want to say so. So this is the general composition. And now if we look into inks which are used today, you can see on the left-hand side for the well-established standard current ink technology, for packaging material, for lamination, you can see there's a variety of binders like PVC, polyvinyl chloride, there's polyvinyl butyral, then there's nitrocellulose, polyurethane inks, or even full PU inks. If you look at the surface printing inks used today, you see that nitrocellulose here again is very important for this approach, sometimes in combination with polyurethanes. And if you look at the raw material class of pigments, we have put here that, let's say, in the well-proven or widely spread inks today, the so-called azochemistry plays an important role in the sense that this pigment chemistry has a very good price-performance ratio, and it's the working horses in this area. Now, having said this, let's say this setup of inks or mix of inks today has some limitations, and you see in the middle the thermal stability, which I mentioned already, because re-extruding, recycling means melting up the polyolefins, polyethylene, polypropylene to temperatures up to 270 degrees centigrade for several minutes. And in order to have an acceptable result, you need high heat stability. And on the right-hand side, you see now how Sigva can help overcome these limitations and help you using more suitable inks. When we look at the binders again on the right upper side, so there we have to take the thermally stable ones, which is the polyurethane chemistry, preferably the so-called aliphatic ones, but also polyvinyl butyral can be used. When it comes to the pigments, you see Sigva is able to offer a variety of heat-resistant inks with high performance. The challenge can be that in terms of color, exact color, color shade, there might be some differences and some limitations. And of course, there is an impact on cost, because these high performance pigments have a different cost level to a large extent. The last product group, just to mention it, is the overprint lacquers. They are not pigmented, so it's transparent functional layers, which often in surface printing can be applied to a given printed design to enhance the technical performance. And what we can offer is also that we offer systems which avoid temperature sensitive systems, which is then nitrocellulose, which would decompose at 250, 270 degrees, and also PVC should be avoided. But we have overprint lacquers in our portfolio, either one component systems or in some instances when you need high performance, high gloss, it's up for a detailed discussion. We could offer two component systems, which means ink layers which are formulated or combined with a hardener based on isocyanate chemistry, and in the two component system, and after curing they have higher resistances. So that's the solutions we could offer to help you make inks more recyclable. And that's already a summary, an overview of what Björn and me wanted to share with you today. Because on the way to increase the quality of recycled plastic material, we see that more and more monoplastic material will show up in the market. And to enable this, Siegwerk offers the right ink formulations, be it here on the top for surface printing with improved mechanical or chemical resistance, be it for the new film qualities for lamination, where we can secure highest bond strength, which meet your requirements. In my part, I have pointed out that we as Siegwerk see a significant benefit in de-inking, and with our de-inkable solutions, we can contribute together with you for an improved recyclate quality, because we can get rid of all the ink components. But since this will still take some time until this can be established in the industry, rather short term, we can also offer inks with a higher heat resistance, with a target that they are re-extrudable, using re-extrudable raw materials, like I have outlined on the last chart primarily. Okay, that was the overview and what Björn and me wanted to share with you. Now there would be the time for questions from your side, and I'm curious to hear from Carla if already questions have arrived in the chat.
Yes, thank you so much. So firstly, thank you so much for this presentation. It's a very important topic, and I think everyone would agree that very valuable content has been presented today. So we are going to now move on to the question and answer session. So I'm going to start reading the questions, and then the presenters will be answering them. So please keep typing your questions in the question box. The first question is, do OPVs negatively impact this process? I'm assuming this process refers to recycling.
Yeah, I assume it's the mechanical recycling process. It can be if you choose an OPV that has a very thick layer, like in particular some UV or something is more risky. But if you go for a, let's say, normal OPV, in our experience, particularly when it's PU based, it blends in pretty well, and you wouldn't get any major lumps or no blocking of sieves or anything. It depends a little bit on the application, as always, and what exactly you do, but in general, it does not have to harm the process. Let's put it that way.
And like I have highlighted, one major guiding principle is avoid thermally unstable substances, and this is nitrocellulose and PVC. But if you avoid this, then we can offer solutions where overprint varnishes don't cause a problem.
Yeah.
Great. Okay, next question. You showed one frozen food pouch sample with heat resistance varnish. If we think about the seal window on the pouch machine, what was the seal window temperature difference with and without your heat resistance varnish?
That's a good question. The details for that, I don't know. Stefan, do you know them?
Yeah. So we didn't investigate to this level of detail, but generally speaking, let's say the impact of an overprint varnish of the heat seal window of a given film, I would say will be there, but it's a minor impact, because if we compare the size of the thickness layer of an overprint varnish, it's let's say 1 to 2 micron, and so the heat capacity of this ink layer is not significant compared to absorption of heat, of course, in the monoplastic, which then melts and has to seal. So the target, so I would say there's a limited impact which we didn't test, but our target is more that we avoid the sticking to it. So that the heat window is only little influenced because the polyolefin has to melt, but we avoid the stickiness, but we don't use up heat to seal.
Yeah, but we can check with our colleagues in South America. They should have the details. So if we get your contact details, whoever asked that question, if you have that your contact details, we can follow up and give you more detailed information. Yeah.
Yes, we.
But it was the message. The main message for us was it came into an area where it's a reasonable process to work with, and that was important because it's not at all possible without the overprint varnish.
Okay, great. Then we have another question about OPVs. Does heat-resistant OPV lacquer prevent shrink effects of PE or PP under heat, or does it prevent sticking to the sealing jaws?
The latter. I mean, you can't keep olefin from melting. So they have their melting point, and when you go past that, they will melt and they will also shrink afterwards. But it prevents the sticking, and it also gives, to some extent, some stability because it's a 2K layer. So it also gives a little more mechanical stability.
Okay, great. Then the next question, does de-inking take a long time to achieve?
Minutes.
Yeah, I can answer. So because we are working on this very systematically for quite a time, and of course it depends, and we see differences. The easiest to de-ink is one component systems, so nitrocellulose, PVB, full PU inks. So and this takes only a couple of minutes. Of course, what we do today is we work also in our lab according to test protocols, be it from the APR or EPBP, where we have a test protocol for 15 minutes max. Then it stops for the evaluation. But there's several ink solutions we can offer which already are de-inked after several minutes. One last remark, because the timing also depends on the exact conditions, and one of course is the temperature and the formulation of the de-inking solution, because next to caustic conditions, detergents are used, and so the exact chemistry, and the last point is also the mechanical, let's say, stirring, because also this stirring speed then will have an impact. But generally speaking, like I said in the beginning, de-inkable solutions only need a few minutes until they can be de-inked.
Okay, great, thank you. Next question. Are there already inks available with the right combination of binders and pigments, or is a new system required?
In principle, it's available, but if you are using an ink from Siegwerk or potentially the competition today, chances are that you will see changes in the shades of the pigments, because we need to use high performance pigments in a basically PU or PVB matrix, and this is going to be different to a whatever 57.1 or whatever magenta shade, for instance. But in principle, those inks are available in Siegwerk, and you could test them if you want. but you would have to test and to approve them.
Okay, great. I think we have time for one more question, and then we've sort of made the end of our session. So if you have one last question, please type it in, but I'll just ask. Here we go. What are the remaining challenges or next steps to fully scale up this more circular laminate solution to the new standard?
If I may ask, or Björn, do you want to?
Yeah, no, go ahead.
Because I've said in my part of the presentation, it's not existing now, these de-inking process in the industry. So what has to be done? We, as an industry, we have to, let's say, convince recyclers that it is worth investing into this path. I'm talking about de-inking now, no? So to make this happen, and we at Siegwerk work, we build up pilot plans to progress more. When this question was more referred to mechanical recycling without de-inking, I think that today we could be much more advanced. That's more about the sorting capabilities. So and we have successful cooperations and projects with customers and market and brand owners where we deal with post-industrial waste, where it is much easier to collect and then to define the quality or to define the quality of mechanically recycled material.
So, but if you ask for the one biggest hurdle, I would say it's the sorting today. And therefore, this is also why we are focusing on post-industrial waste for now, because there you have pure material to begin with. As soon as you go post-consumer, it's a challenge to really sort the material to an extent that you get out a reasonable quality out of the mechanical recycling, and you also have to clean it. And don't forget that post-consumer waste is very dirty, contains food and other residues. So that's, if you ask for the biggest hurdle, I would say this is the biggest hurdle.
Yeah.
Okay, and then I think we have just one more question, and then we can end it. The question is this technology, I'm assuming they are referring to de-inking, limited to flexible packaging or also suitable for rigid PE and PP?
Should be suitable. It depends on the ink chemistry that you use to print on these other webs. But in principle, it should be able to apply that to all kinds of webs that are not moisture sensitive. But for paper, you have a different process altogether anyways.
No, but I can only agree it should be suitable, and it could be even more worth doing it, because on rigid, the film thickness of the material that you win when you de-ink it is even higher. So therefore, in terms of cost, and also when it's about drying of de-ink material, it's can be even more economical doing rigid than looking for very thin flexible packaging substrates. So therefore, I would agree that it is a viable path as well.
Okay, and that brings us to the end of today's webinar. So I would once again just like to thank everybody for attending, and also a very special thank you to our speakers for today. And I hope that everyone enjoyed the session. As I said, a recording will be available after this. And if you have any other questions, you should have my email address, and you are very welcome to get in touch with me directly. Other than that, thank you so much, and I hope you have a wonderful weekend. Goodbye.
Thank you very much, everybody. Goodbye.
Bye, everyone.